All right, Math 2, here we go. We got lesson 2.2.2, more conditional probabilities, day 2. I'm going to really have to pay attention because this is my third take because I wasn't paying attention while I was doing my work earlier. All right, here we go. Raul is conducting a survey for the school news blog. He surveys 200 seniors. Okay, that's the total. That's a grand total. And finds that 78 of the students have access to a car on the weekends. So some of them, 78, can get a car on the weekend. 54 students have regular chores to do at home. So that would be chores in car and chores in not car together. So that would be 54 over here. And then 80 students don't have a car and they don't have chores. So that would be this one right here. This is the and, where 80 of them don't have either one of them. Now we can fill out the rest of them because we know that the totals have to add up. So if there's 54 here with chores, then that means there's 146 that don't have chores. And over here, since there's 78 with a car, that means that there is 122 who do have a car. Okay, now I can figure out that up here, that this number up here has to be 42, because 42 plus 80 is 122, so they have to add going up and down. And then I can say, okay, going this way, this has to be 12, because 12 plus 42 is 54. And then going this way, this would have to be, what, 66? Because 12 plus 66 is 78. And then going this way, I can see that it still adds up, 66 plus 80. So everything has to add up. Is there association between car privileges and having regular chores, or are they independent? So if they're independent, we would say that the probability of A should be equal to the probability of A given B. So let's call having a car A, and let's call doing chores B. So if these two probabilities are equal, they're independent and they're not associated, meaning that one's not causing the other to happen. If this is not equal, then they are associated. One is affecting the other. So if there's an association, it means whether or not you have a car is going to change whether or not you have chores. It affects it. So let's find the probability of A having a car. Having a car is 78 out of 200. Probability of A given B. So B we said was having chores. There are a total of 54 people who have chores. So that's our denominator because we're only looking at the people with chores. And of the people with chores, how many of them have a car? 12 of them do. So now we want to see if those two are the same number. So we're going to do 78 divided by 200. And that gives us 0.39. So 0.39. And then 12 divided by 54. We end up with 0.2 repeating. So 0.22. These are not the same. Therefore, they're not independent. Independent means they're not affecting each other. So these ones are associated. One is affecting the other one. If they were independent, we'd say they're not associated, they're not affecting each other. All right, next one. 30 students in Mr. Holcomb's class. Okay, so here's my total of 30 students. Looks like I got 18 boys and 12 girls. So boys and girls. Total is 18 of the boys, and looks like there are 12 girls. Okay, I choose a student at random to present their problem to the class. So I'm going to have them present. And some of them have not presented. Now it looks like so far 4 boys have presented and 3 girls have presented. So that's a total of 7 people that have presented, meaning that 23 have not presented. Going this way, if there's 18 boys and 4 have presented, then 14 have not. If 3 girls have presented and there's 12 girls, then 9 have not. And here we got 14 and 9 is coming out to 23, so we've got it set up. So that's one way you can do it. This is set up with the totals in there, but these are not the probabilities. The probabilities, like if we wanted the boys, we'd say 4 over 30, and that'd be the probability of boys that presented. So what we can do is set it up with the probabilities instead. When we do probabilities, the probabilities always have to add up to 100% or 1. So over here, the boys that presented, there's 4 out of 30. So I'm just going to put that 4 over 30. 3 out of 30 of the girls. And then this is a total of 7 out of 30 have presented. 14 boys have not presented, so that's 14 out of 30. 9 girls have not presented, so that's 9 out of 30. And then there's a total of 23 out of 30 that have not presented. Going across the other way, we see that this boys is 18 out of 30 and girls is 12 out of 30. 18 out of 30 plus 12 out of 30 is 30 out of 30, 100%. 7 out of 30 plus 23 out of 30 is 30 out of 30, 100%. So this one just has our probability, and this one has all of our individuals in there. Find the probability of boy and presented. Boy and presented, here's the probability. So it's kind of nice having it like this because we already have our probability sitting right there. So that would be 4 out of 30, which is 2 out of 15. Girl or presented. Girl or presented, we're okay with these two probabilities and this one. So boys that presented is okay because they presented. Girls that presented is okay. And girls that don't present are okay because I'm looking for anybody that's presented or anybody that is a boy. So presented or a boy, both of them. Oh, wait, which problem am I on? Dang it. Oh, I'm on girls and already presented. Okay, so the girls presented, these three probabilities together. I almost screwed this up a third time. So we get a total of 16 out of 30, which is 8/15. Girl, given that they already presented. Okay, so given that they already presented, 7 out of 30 have already presented. So that's our denominator. We're only looking at 7 out of 30 of them. Girls that already presented is 3 out of 30. And when we have complex fractions like this, we talked about it earlier, that you can just multiply the top and bottom by 30, and we'd end up with 3 over 7 as our probability for that. All right, back page. Let's see if I can do this right this time. Keeping fingers crossed. All right, so this one says, if Letitia studies for her math test tonight, she has an 80% chance of earning an A. And if she does not study, there's a 10% chance of her getting an A. Whether she studies or not depends on if she has to work at her parents' store tonight. This morning, her father told her there was a 50% chance that she needed to work. Okay, so studying is dependent on her working. So if she works, she's not going to study. So we'll call this work or not study. And then no work, that means she's going to study. All right, and there's a 50% chance that she's going to do one or the other. So she's got a 50% chance, 1/2, and a 50% chance, 1/2, that she is not going to work. So she's not going to work or study, and work but not study. Now, our percentages are different depending on if she's going to work or she's not going to work. So we're going to look at, is she going to get an A or is she not going to get an A? Okay, so these are going to be different based off of whether she studied or not. So let's go ahead and look at this part here about her studying. So she doesn't have to work and she's going to study. So it says that she's going to study. She's got an 80% chance of earning an A. So we could say that's 0.8, or you can say that's 8 out of 10. Or you can just call that 4 out of 5. So if she has an 80% chance of getting an A, then she's got a 20% chance of not getting an A when she studies. So 20% chance, or we could call that 1/5. The probabilities change when she doesn't study. When she doesn't study, there's a 10% chance of her getting an A. So that's 1 out of 10 when she does not study. That means there's a 9 out of 10 chance of not getting an A when she doesn't study. So half the time she's not going to study, half the time she's going to study. So here we can do 1/2 times 1/10 and get 1/20. Over here we can do 1/2 times 9/10 and get 9/20. Here we've got 1/2 times 4/5, and that gives us 4/10, which reduces to 2/5. So 1/2 times 4/5 is 4/10, which is 2/5. And then over here, 1/2 times 1/5 is 1/10. All right, so now at this point, remember on these types of problems, it's nice if you have the common denominator. So let's look at our biggest number, 20. Does 5 go into 20? Yep. Does 10 go into 20? Yep. So 20 should be our common denominator. So at this point, I've got 5 is being multiplied by 4, so this is 8/20. And then this is multiplied by 2, so this is 2/20. And add all these together, 1 plus 9 plus 8 plus 2, you do get a total of 20/20. It's all adding up to 100%. All right, what's the probability that Letitia gets an A? Well, there's 2 ways she can get an A, by not studying or by studying. So there's a 1 in 20 chance and an 8 in 20 chance. So we'd get a total of 1 plus 8 over 20, which is 9/20 of the time, 45% chance of getting an A. What's the probability that she studied given that she got an A? Okay, so we're looking at if she got an A, only at if she got an A. So the total of her getting an A is 9 out of 20. That's our denominator. And what's the probability that she studied? So if she studied, that's 8 out of 20. And again, we can multiply the top and the bottom by 20, and we would end up with 8/9. There you go. There is your math for today. All right, math hard. See you guys later. Bye-bye.